The timing of this event is great. Quantum theory was developed about 100 years ago, and still in some ways is mysterious even to experts. And that's something we'll talk a little bit about. At the same time, recent developments have brought us to a place where scientists and engineers are using quantum physics as a tool to make more discoveries and to supercharge progress in areas such as computing and material science. So we'll talk about that too. There is, in my opinion, kind of a dichotomy there between what physicists understand and what they are able to predict and control. That dichotomy would be at least part of my answer to the question of what does it mean to live in a quantum world. But there are 5 other people here tonight who are, at least, well, there's probably more, but there are 5 people who are going to be on this stage who are far more qualified to speak to that question than me. I'm honored to be joined here this evening by 5 experts whose areas of expertise run the gamut, from deep philosophical implications of quantum theory to the ways in which the theory's puzzling powers are now being harnessed to solve practical problems. So I think what I'll do is I'll introduce each person, and maybe as I do, they can come to the stage and take a seat. I'll come up here too. So David Albert has a PhD in theoretical physics and has been a professor in both physics and philosophy departments. He has been at the philosophy department at Columbia University since 1987, and he is a co-founder and co-director of Columbia's master's program in the philosophical foundations of physics. He's the author of 4 books: Quantum Mechanics and Experience, Time and Chance, After Physics, and most recently, A Guess at the Riddle. Katiuscia Cassemiro is the chief editor of the PRX Quantum Journal, published by the American Physical Society. Katiuscia works on publishing research articles and helping to disseminate the knowledge to a broader audience. She has vast experience in cutting-edge quantum research and technology, having implemented several photonic platforms enabling new studies of quantum properties of light. Katiuscia joined the Physical Review as an editor in 2015, and since then has engaged with the top experts in the field to assess the quality of the latest research. Anna Grassellino is a senior scientist at Fermilab and the director of the Superconducting Quantum Material and Systems Center, one of the 5 national quantum centers funded by the Department of Energy. Her research focuses on radio frequency superconductivity. Grassellino is a fellow of the American Physical Society and the recipient of numerous awards for her pioneering contributions to SRF technology, including the 2017 Presidential Early Career Award and the 2023 New Horizons in Physics Prize by the Breakthrough Foundation. Philip Kim. Philip Kim is an experimental condensed matter physicist at Harvard University. His research is focused on the study of quantum phenomena in low-dimensional materials, including atomically thin graphene. And finally, Robert Konik is a theoretical condensed matter physicist whose interests are primarily in the physics of materials, where strong electron-electron interactions give rise to exotic effects. He trained as a high-energy physicist, and he often uses the techniques of quantum field theory to understand this behavior. He has been at the Brookhaven National Lab for the past 20 years and is currently serving as chair of its Condensed Matter and Material Science Division. We're going to take tonight's topic in 3 chapters. Chapter 1 is what living in a quantum world means. Chapter 2, we'll talk about cutting-edge applications of quantum theory, and we'll finish with Chapter 3, which will address what the theory says about what the world is really like and what our role in it is. But first, each panelist is going to take a few more minutes to tell you a little bit more about their work and how it relates to quantum theory. We can turn on the slides. And we'll start with David.
Great. Is this on? Yeah? Yeah. Good. I think I'm the only member of the panel who's currently a Columbia faculty member. And so I just want to take a second before we start to acknowledge what's going on across the street. I don't want to make a speech, but I guess I feel compelled to say a tiny bit. I deeply disagree with many of the student protesters who are now being arrested by the New York City police. I think many of them are confused and misinformed. I think many of them are morally irresponsible. But the act of calling the police, the municipal police, onto campus to deal with a one-day-old, nonviolent student protest, which is not, insofar as I know, impairing the normal operations of the university, strikes me as a dangerous abuse of power. I was 14 in 1968. I remember those events here. And at that time, even though the student protests had completely shut the university down, it took the university administration a full week to call the police onto campus. And that act is nevertheless remembered to this day as a low point in the history of our university. And I'm sad to say I think we've lived through another such low point today. Anyway, that's... Thank you. So I've spent most of the past 40 years thinking about a bunch of connected questions about the foundations of quantum mechanics and about the nature of time and about the architecture of a comprehensive scientific account of the world. That is, about how the various aspects of the scientific account of the world all manage to hang together. Much of my work on the foundations of quantum mechanics has been concerned with the business of trying to solve something called the quantum mechanical measurement problem, which I hope to tell you a little bit more about later on in the session, and more recently with questions about what it is that quantum mechanics seems to be suggesting about the nature of the fundamental stuff, the fundamental substance that everything in the world is made of, and about the nature of space. The work on time has to do with the relationship between thermodynamics and statistical mechanics and the question of the difference between the past and the future. And the work on the overall architecture, the scientific picture of the world, has to do in particular with the relationship between fundamental physics and all of the other sciences. Chemistry, for example, and geology, and meteorology, and biology, and psychology, and sociology, and economics, and so on.
Thank you, David. Next is Katiuscia. And do we have a slide controller?
So it's working, right? Yeah, so I joined the quantum community several years ago, and I just thought of mentioning how I got engaged with that. And it was during my undergrad, so I started to study, I visited a lab where they were doing some experiments with a squeezed vacuum. And they were aligning some mirrors, and I thought, okay, to me, vacuum is the same as nothing. Why are you aligning mirrors to measure that? And they were squeezing. I was told it was something. It would meant that this vacuum would fluctuate less than what you could see classically. And the whole thing was very bizarre to me. But I thought, well, aligning mirrors cannot be that difficult, so I would just start doing that and see what it really means. And from there on, I just did my PhD in quantum, measuring entanglement, postdocs, and so on. Can you change the slides? Okay. And so for this audience, I thought of also giving the message that if you like quantum, I think anyone really can study that. You don't need to be super smart. So I come from, I lived most of my life in the central part of Brazil, which is the same to say that it's the middle of nowhere, really. There are no other PhDs in my family. My grandparents lived in a house like that. And I was not doing experiments with science as a kid, though I really loved to be out in nature. And so, yeah, if you like quantum, I mean, of course, it will take some years, but you can just start to study, and I'm pretty sure you can be a specialist as well. So, yeah, I did my undergrad and PhD in São Paulo, then I went to Italy, and in this context for this community, I was in Italy as well. And then at some point, I moved here to the US to work as an editor. So, can you change again? So what I do now, I'm not actively doing research anymore, but I am an editor for this journal from the American Physical Society. We publish everything in quantum physics. The one thing I want to say for this audience is that the role for editors is that we have an oversight, we take care that all the research results, they are substantiated, that all the information is in there for people to want to rely on the results, to trust it, and to be able to eventually repeat the experiment as well, or use this theory for something else. So that's the role of the editors.
Thank you. Next is Anna.
Hi, everyone. Let me say, first of all, I'm very excited to be at the Italian Academy. I'm Italian myself. I think I heard there is in the audience students from Catania. I'm actually from Marsala, so that's a small word. I came to the United States many, many years ago. I did my PhD at University of Pennsylvania. I studied in Italy at University of Pisa. I am a true quantum person in a superposition of engineer and physicist. And I'm a senior scientist at Fermilab. Fermilab is one of the national laboratories funded by the Department of Energy. We are kind of the sister lab of CERN. We build the giant particle accelerators. And my specialty is actually in the building blocks of particle accelerators, which are superconducting cavities. Turns out the superconducting cavities can be used to build particle accelerators, but also to build quantum computers. So that's why I'm here. I serve today as director of one of the 5 national quantum centers that are funded by the Department of Energy. This is what you see here. SQMS is a collaboration of over 500 researchers that come together across academia, national lab, and industry to really join forces in multidisciplinary collaborations to advance quantum technologies and applications of quantum. If you can go to the next slide. What we do at SQMS is really push the big challenges that we have in terms of advancing quantum, the fundamental building blocks of quantum computers. And in particular, we focus on particular platforms that are based on superconducting technologies. And we go all the way to bring together the theorists and the experimentalists and the people who really are experts in the materials, in devices, and all the way to the people who are actually the users that really want to understand how to use quantum computers or quantum sensors. Next slide. This is kind of like what my past few years have been and what my next years are going to look like. I'm very excited to bring together this collaboration that is really doing what a little bit of, I think it went away, but okay, a little bit of what I told you, which is going from advancing quantum technologies for sensing and for computing, again, from the materials, all the way building prototypes of quantum computers, and then building these ginormous facilities, and I guess we'll get to talk a little bit about this, that can really enable some applications. In particular, as Fermilab, we are very interested in, I think I have a fellow high-energy physicist here, how can we use some of these quantum computers to solve some very challenging scientific problems in particle physics or in condensed matter physics. So that's a little bit who I am and what I'm doing.
Thank you, Anna. Next is Philip.
Okay, so I'm Philip Kim, currently at the Harvard University in the physics department. I was at Columbia University about 10 years ago before I moved, and I had a quite a long time collaboration with Professor Alberto Morgante, and that's probably the connections with the Italian Academy. So I've been working on this, the particular system called the quantum materials, and more precisely low-dimensional quantum materials, like the graphene, a very thin sheet of the carbon atoms. And some other similar type of the atomically thin materials where the quantum confinement provide the very exquisite the quantum properties of the materials, often this can be quite useful for studying their properties as well as using them for some of the quantum devices. If we go to the next slide. So that you can see that some of the examples that how we can kind of combine this material with the device structures, and one can study about their physical properties, but also sometimes this device can be useful for platform to realize some of the quantum technologies, and that has been some of the my interest. And today probably I'm going to cover onto some of this material aspect as well as some interesting quantum properties arises from these materials.
Thank you. And last is Robert.
So I'm Robert Konik, and so I'm probably here because I've spent a lot of time in Trieste, and I know very well Andrea Tramontoni and other researchers at the ICTP and at CISA. I think it's that connection that's got me here. In fact, I've spent so much time in Trieste that I even have an Italian tax ID. So I'm a condensed matter theorist. However, I was trained in the other big area of physics, high energy theory. My graduate student advisor, André Leclerc, was a string theorist of all things. Which string theory is one of the possibilities for a consistent theory of quantum gravity. However, I wasn't really so much interested in that. I was interested in using the techniques of string theory to study condensed matter systems. And so I did that when I was a graduate student. I continued to do that when I was postdocs at Santa Barbara and at the University of Virginia. And then I moved to Brookhaven, and my interest in material physics grew. And so more recently, I've been interested in how to use artificial intelligence to improve our understanding of material properties, to discover new materials. I'm also involved in projects which you could say are developing theoretical tools to better understand the quantum properties of real solid-state materials, something that's non-trivial to do. So I'm active in research, but I also have another hat. I'm chair of the Condensed Matter and Material Science Division, so I help oversee at Brookhaven National Lab the DOE's efforts in material science and help form the directions that it will take at the lab.
Thank you, Robert. We can turn off the slides and we can draw the curtain as well. We're going to scooch the chairs more to the middle. I think I'd like to be on the end, if that's all right.
Yeah,
You guys-
sure. We could adjust. He likes his own.
There we go. So, chapter 1. We're going to talk about what it means to live in a quantum world, and I want to ask David maybe to start us off by just telling us what is quantum theory to begin with, and how is it different from the physics that governs our everyday experience and the things like the way a baseball traces a parabola when it's hit. What makes quantum physics different from what we're familiar with?
I'll be very brief, needless to say, or as brief as I can. At the beginning of the 20th century, it became clear that classical physics, the physics that is of Galileo and Newton and the 19th century accounts of electricity and magnetism associated with figures like Michael Faraday and James Clerk Maxwell, were not going to be able to account for the stability of atomic matter. Experiments by Ernest Rutherford and others had revealed that atoms consisted of negatively charged electrons orbiting around positively charged nuclei, and the theory of Maxwell and Faraday unambiguously predicted that such electrons would shed their orbital energy in the form of electromagnetic radiation very, very quickly and crash into the nucleus, and the familiar world of tables and chairs and people and buildings and planets and so on would almost instantaneously cease to exist. So a new theory clearly had to be developed, and such a theory was developed over the course of the first 30 years or so of the 20th century to account for the stability of atomic matter, and more generally for a host of very strange behaviors of subatomic particles that were being discovered at that time. And the theory that emerged, which was called quantum mechanics, turned out to differ in very deep and very radical ways from the classical physics that came before it. And it differed as well from any of the ways it's fair to say that anyone had ever previously imagined that the world might be. Quantum mechanics, as it's standardly presented in textbooks, entails, for example, that an electron which can be located here or there can also be in a very mysterious and unfamiliar condition, a condition which is referred to as a superposition of the electrons being here and the electrons being there, in which the very question of whether it's here or there somehow fails to make sense. A condition, that is, in which asking whether the electron is here or there is something like asking whether the number 5 is married or single, or like asking about the weight in grams of Catholicism. And quantum mechanics, as it's standardly presented in textbooks, entails that a pair of particles can sometimes be in a condition which cannot be described by describing the conditions of each of those particles separately, a condition which is referred to in the literature as entanglement. And quantum mechanics entails that what happens to one of a pair of entangled particles can affect the other particle in that pair instantaneously, and no matter how far apart in space those two particles may happen to be, and no matter what might interpose itself in the space between them. And quantum mechanics entails that no measurement of an initial state of an isolated physical system, no matter how extensive and how precise, can put us in a position to predict the outcome of certain later measurements on that system. Quantum mechanics seems to suggest, that is, that there's a fundamental and ineliminable element of chance in the evolution of the world. Of course, one of the things that this new theory had to do, if it was going to count as a serious candidate for the fundamental physical theory of the world, is to tell us why we had never noticed all of these strange things before. And quantum mechanics is indeed structured in such a way as to guarantee that the predictions it makes about the outcomes of familiar sorts of measurements on familiar sorts of macroscopic objects, rocks and projectiles and planets and levers and pendulums and all of the traditional staples of classical physics, in familiar sorts of circumstances will more or less line up with the predictions of classical physics. But quantum mechanics also shows us precisely where and precisely how to look for these much less familiar and much more mysterious sorts of behaviors. And the new technology that we're going to be talking about today has to do with looking in precisely those ways, in precisely those places. And there's one more thing worth mentioning here. Consider how it is that I know that there's a table to my left. Physics has always offered us a sketch of an account of an answer to that question in the following form. There's light in the room, and some of the light reflects off the table, and some of the light that reflects off the table enters my eye, and some of the light that enters my eye impacts on my retina, and that causes various sorts of electrical excitations in my retina, and those electrical excitations cause various sorts of electrical excitations in my optic nerve, and those excitations cause various sorts of excitations in my visual cortex, and all of that eventually ends up putting me in the brain state that undergirds the phenomenal experience of seeing that there's a table next to me, and it goes without saying that it's been terribly important to all these accounts that each step in the chain that I just described occurs in strict accordance with whatever the fundamental laws of physics are. And one of the deepest problems at the foundations of quantum mechanics is that we don't know how to sketch an account like that, even in the vaguest and most schematic terms in the context of quantum mechanics. And the problem of producing an account like that in the context of quantum mechanics is called the problem of measurement, which I think we'll be talking a little bit more about later on in the session. Thanks.
Thank you, David. Anybody like to add to that? Make any comments about that?
It's hard to follow.
So you said something that was really important early on, which is that that quantum theory was developed in part to just explain the fact that the world doesn't collapse on itself. Right. So in a sense, it's necessary for
very much
everything we see around us to be the way it is. On the other hand, the randomness of it, the fact that particles can act as though they're in two or more places at once, the fact that particles can be entangled with one another and seem to communicate across infinite distances or very large distances instantaneously. All these things are not, they feel very unfamiliar. Why is that? Why?
Well,
yeah.
Like I said, and this is characteristic of several developments in physics in the 20th century, not only quantum mechanics, but also the theory of relativity. These theories are reactions to various crises in the capacity of classical physics to explain the results of experiments. But the obvious constraint on the development of new theories to explain the results of those at the time exotic experiments was to account for the fact that classical physics does as well as it does with familiar sorts of physical systems under familiar sorts of circumstances. So it's a constraint on all these theories. In the context of quantum mechanics, this constraint was sometimes called the correspondence principle. When people were developing quantum mechanics, when people were experimenting with various forms of quantum mechanics, they always knew that among the things they were going to need from the theory they ended up with was some theory that, as I said, explains why classical mechanics does as well as it does across the wide range of familiar sorts of physical systems under familiar sorts of physical circumstances. So of course, the theories constructed that way contain a ready-made explanation for why we haven't noticed these strange things before. And they ought to, because the historical fact is that we didn't notice these strange things before. And quantum mechanics had better be able to explain that and yet be equal at the same time to the task of explaining the very bizarre, very non-classical, very unfamiliar sorts of behaviors that we see if we learn to probe nature at the right places and in the right ways.
Anybody want to add something?
Yeah, I don't know. I just, even though, yeah, we say it's unfamiliar, but I think a little bit, if you think of waves, right, and we can try to have a little bit of a sense of what's happening, maybe I could try some. So if you just think waves in the water, and if you know what is interference, so if you see two waves coming together, and that's going to form a different pattern, that is not the pattern of just one or the other, but that is something else that comes out of the two together. So one of the things in quantum theory is that those types of waves, they're going to give you some description of the system, and essentially they're going to give you some sort of probability of the results that you can get from the quantum system. And I think what's interesting in this picture also, when you just try to think in those ways, is that we also know that waves, they're going to interfere only if they are indistinguishable, so if you cannot tell them apart. So if I take a laser that is red and a laser that is green and put together, they're not going to interfere because you can tell which one is one. So in this same sense, when you have, if you think on a quantum system, if they are now in touch with the environment in some ways that you can tell apart what is the wave, so if you're watching the environment and this gives you information about the wave, you are losing this property that they are indistinguishable, so you can tell them apart, and then they don't interfere anymore. And so because you lose the capacity to interfere, then you go back to the classical state of things. And I think what is also nice on that is if you think now in quantum algorithms, what are those? You could again think in terms of those waves, and you say, well, if you have the waves interfering, you have so many possible interference patterns that are available out there. So this gives you a lot of possibilities of calculations in a way, if you think all your calculations are coming from possible interference patterns. So what a quantum algorithm will do is that you have a sequence of steps that you try to prepare some interference pattern that is such that you create some sort of interference that the results that are not part of your problem, they're going to be suppressed, and everything that builds up from the interference, this is going to correspond exactly to the solution of the problem that you wanted from the beginning. So a quantum algorithm is going to be that. What is the sequence of steps that you do so that in the end you have this interference that is highly, gives a high probability on the solution of a problem and suppress everything else. So I think what I'm just trying to say is, yes, there are many things in quantum mechanics that you don't understand, that are not intuitive, but at the same time, if you know about waves, you get a little bit of a grasp initially of what can come out of that.
What you were just describing was how a quantum computer could be used to do calculations.
Yeah,
So we'll say more about that in the next section. But are there more familiar technologies now that rely on understanding quantum theory that wouldn't be possible without all this weird behavior, and that you would point to as sort of, we can do this now because we understand this strange quantum behavior underneath the hood?
Well, I can say that most of our modern day electronics depend on quantum theory. The theory that governs solid state materials is quantum in nature. Usually the aspects that we were just talking about, like entanglement, coherence, are not necessarily emphasized, but all of our modern electronics depends on the ideas of quantum mechanics as applied to these materials. So it's one thing I would maybe want to follow up with David.
Yeah.
So I would consider myself a professional physicist. So some of these weird oddities of quantum mechanics, quantum theory, professional physicists don't spend most of us don't spend a lot of time thinking about this. We just use quantum mechanics to proceed and to try to understand things, but we don't ask deep philosophical questions about what is actually going on. In fact, I would say to some degree, it's actively discouraged by our colleagues.
By funding agencies.
And yeah, you definitely would be very, very hard to try to get something funded that was dealing with the foundations of quantum mechanics. I have a colleague at Oxford who tells his graduate students when they ask such questions just to shut up and calculate.
Shut up and calculate.
Classic phrase.
I can add on a little bit. I think I agree with David that when the quantum mechanics really started out, there are many things that many experimental observations couldn't be explained in terms of classical physics. Black body radiations and some of the spectrum coming from these atoms and molecules, I think those kind of discrete levels without kind of different type of set of the understanding is very difficult, and that's kind of where the quantum mechanics spawns. And consider a lot of the unusual physical interpretation is needed. I think superpositions, entanglement, and those kind of things considered. very bizarre the phenomena and measurement and the wave function collapsing. Those kind of things is something kind of deeply philosophically rooted. And initially, that was something that indeed either you have to take on and just kind of believe and calculate it. But as the technology developed now, I think some of this deep philosophical question is also getting to the more of the experimental regimes. For example, superpositions, entanglement is readily happening in the quantum optics area. When you get into the quantum computing, for example, we will discuss it later, this decoherence and those kind of phenomena is deeply related to what is the meaning of the measurement. So some of these philosophical questions eventually kind of can come to the more of this tight scientific scrutiny in the advance of the technological advance of the experimental tools and something. So I think those kind of deep questions that initially asked, some part is being now also kind of getting into the more of the quantitative experimental the area that one can explore. So that's something that I want to kind of add up.
Just a quick follow-up on that as a concrete example. The first suggestion of the possibility of something like quantum computation a long time ago by David Deutsch, a researcher at Oxford, was a very direct spin-off of work that was trying to get to the bottom of foundational questions about quantum mechanics. Yeah.
Just very briefly to resonate with everything that was said, quantum, you ask us, what does quantum, why do we live in a quantum world?
I did want to ask that next. Maybe we could start with you in terms of what is that, when you think of that, what does that phrase mean to you?
Well, first of all, I live in a quantum world because that's my job. That's what I have to do.
It pays the bills.
But I mean, also as a physicist at a national lab such as Fermilab, where we build particle accelerators to study really the nature of particles, of course, everything at that level is based, as my colleague here said, on the laws of quantum mechanics. Everything that surrounds us, and again, just as it was said, our phones, transistors, it all works already thanks to laws of quantum mechanics. Someone in the audience said tunneling before. That's the first quantum revolution. And then there is the second quantum revolution, which is what we are about to also talk about next, which is how do we then use these properties of entanglement and superposition to advance information, to advance computing and sensors and so on.
Thank you. Robert, what would you say the phrase living in a quantum world means to you?
Well, I'd say at least in part, practically it means this revolution of technology that quantum mechanics is enabled. And it's not just the technology that it's enabled, this technology has shaped how we live and what kind of societies we live in, how we communicate, how we work. And so it's really, since it doesn't happen all at once, it's happened over decades. But if you compare now to when I was born in 1968, I think it's a much different way of living.
Okay. Katiuscia.
Yeah, I think so. Nature is quantum, so I don't have a choice, right? So, but as we were saying, I think all the semiconductors, all the computers that we have now, they're based on quantum. So I don't think there is a single product that you buy nowadays that's in this sense based on quantum, right? So the list, you use your bank account, and they have computers there as well. So all the economy that we have is already based on quantum mechanics in some ways. So if you use your GPS to find this building, you're using signals from satellite that have atomic clocks. So there is quantum mechanics as well. But then, yeah, I think what most people are talking about is more those new quantum technologies, which then use another fact that is quite important, that the quantum theory is already an information theory. So I think this is one very important aspect that was not used in those previous technologies, and it's what people are trying to harness now, this part that there is some information in your quantum state, and you can use it in new ways and explore this entanglement. That I don't know if we're going to address the entanglement, but I could also talk a bit about that later. Yeah.
Okay, great. Philip?
I think think it's already mentioned. I don't have to add too many things, but I think maybe many years from now, I think if you just look back at the beginning of the 20th century, that was a really some new first quantum revolution is shaping up about 20 or 30 years. Maybe many years from now, maybe seeing that this kind of around this time is around the second quantum revolution, who knows? I think if that happens, it's more of this controllability and technologies based on the quantum mechanics that really pops up and becomes kind of readily available. So we'll wait to see.
Great. David?
I also don't have too much to add to what my colleagues have already said. I mean, there is this technological business of learning to locate and amplify and exploit this radical non-classicality of the microscopic world so that it can be made to serve an enormous variety of practical macroscopic purposes. There's also a task that's interesting to some people of a sort of philosophical task of coming to grips with the fact that the world turns out to be profoundly and radically different kind of place than we had previously imagined. What the consequences of that task are on a sort of worldly level, on a practical level, it's hard to say. Although I guess you can say that last time this happened with the scientific revolution of Newton and Galileo, that is, last time it was sort of thrust in our face that the world turns out to be a profoundly different kind of place than we had imagined. Arguably, the consequence was the Enlightenment, was the rise of modern liberal democracy that frighteningly seems to be so spectacularly falling apart right now. So there can be all kinds of consequences of these kinds of reflections down the road.
Thank you. That's great. Why don't we go to chapter 2 and talk about applications? A couple of times the phrase quantum revolution as second quantum revolution has been mentioned. And I think, Katiuscia, you're in a great position as an editor of one of the major quantum journals to maybe tell us what the current trends are, what's happening. Is there something special happening now? Is it a good time for quantum theorists and quantum physicists, and what's hot?
Okay, so maybe I start a few steps back. I think there is a great quote from Ivan Deutsch. He said that quantum mechanics is an enabler. And I think what I like on that is it tells a little bit of the story, like when we started early on in the theory and start to say, oh, there are so many things that quantum theory doesn't allow us to do. And you have this fragile quantum state. When you try to measure it, you destroy it. And it seems like there are many things you cannot do. You cannot copy a quantum state. But then I think what is interesting is that then the community turned it around and said, for example, well, if this is so fragile, then maybe if you're using a quantum state, let's say for communication, the fact that if it's fragile means that someone getting on the line, some eavesdropper, would cause a red flag because it's disturbing this quantum state. And so you have a clear red flag that there is an eavesdropper. And so that means you could use this to make communication safer. And in the same ways, I think also early on, Feynman was also discussing, well, this quantum state is so complex, there are so many things in there. So then how about if you now use all of this complexity, you don't try to describe your quantum system, this would be way too complicated, for example, but if you can control it in the lab, maybe you can use it for doing your calculations since it has so many information contained on it. So I think for a while this was all kind of hand-waving, but then I think one of the big breakthroughs was actually when Shaw came in 30 years ago, I think. And he was able to show that actually, he concretely showed that there is an algorithm, a way to use quantum states to solve a very important problem, the factorization problem. And so what he shows is that, yes, if you are able to control the quantum state, you would factorize in a way that is exponentially faster than what you could do in a classical computer. So there is a big speed up. But not only that, also, this is a very important problem, factorization, because all the classical communication that we use nowadays, the security, is based on the fact that it's very difficult to factor big numbers, to find the prime factors. And so if you're now saying, well, this problem that is so difficult, you base your security of your communication on that, and now suddenly this problem is not difficult anymore, you're saying that you can solve it very easily, fast. This is a big threat for communications. And so, and the fact that he showed this very concrete algorithm, how to do it, I think it was one of the big pushes for the community to start to pay attention. But still, from that to being able to do in the lab is a big step. And so at the time also people thought, yeah, okay, there is this great theoretical idea, but people are not going to...
Just to, in case some people aren't familiar with the idea, this is the idea that in 1995, this physicist Peter Shor developed in theory, not with a machine, an algorithm, like basically the code or the software that could run on a special kind of computer, a quantum computer, that could...
If you would have a quantum computer,
if you did have a quantum computer,
but
you could run this,
yeah.
and you could figure out for a big number that was produced by multiplying two prime numbers, you could figure out what those prime numbers are. And that's important because that's how communications and security systems encrypt information nowadays. And so that could unlock and break that kind of encryption. So this was an idea, and it was also a demonstration of how powerful the idea of quantum computing could be.
Yeah, exactly. Yeah, thanks. But then, I think from that it was a big step for people to say, yeah, great idea, but how you're going to do that? We are not able to do that in practice. Again, quantum states are fragile and so on. So I think what we observe from that to now is more people, a lot of work went on to try to control those quantum systems in the lab, to be able to reach high levels of quality on those systems and being able to really play around with it in ways that preserve the quantum properties of the systems. So there are many Nobel Prizes just on that, on trying to control the systems. But still, one other important ingredient that also came with Shaw and also Steen a few years later was that if you want to use this to process information, you need also to find ways to correct for errors. So if you are even in a classical computer, errors can occur. You need some algorithms to correct for that. And it was not clear how to do that. So I don't know, maybe I just give an example. If you're in a noisy environment and you want to communicate with someone, what you do, if you just speak normally, nobody's going to understand you. You could kind of scream, but that's not very efficient as well. You're going to get tired. So what you do, you use redundancy. You repeat what you're saying more times. And with that, because of the redundancy, someone is then going to be able to understand you. So more or less, this kind of the idea for error correction in general.
This is the essential problem with building a quantum computer, right?
Yeah, so you need to do this error.
The randomness of quantum theory or quantum mechanics means that you end up getting errors in ways with higher, frequency than you would in a normal computer?
Any process in classical as well. You always have some errors and you need to be able to correct for that. But
it's a bigger problem in quantum computers,
Well, people didn't know how to do. So then it was another breakthrough, coming up with the ideas on how to do. And what we see a lot now is how you connect that to the real hardware, so the real quantum systems in the lab, how you convert those highly theoretical ideas to something that people can do in the labs. Maybe I could say more, but let's do other.
Okay, so I mean that's a big theme right now is quantum computing. I see articles and news releases about this all the time. And Anna, your institution is working on elements of this. Maybe you could tell us, why is it that we don't, how is a quantum computer different from a regular computer, and why don't we have them now and on our desktops? And when will we? How is that going to happen? We now have some kind of quantum computers, right? But we're not really all the way there. So,
well, first of all, let me say, we scripted a little bit the questions before with Bob, and when Bob assigned me this, I was very thankful because I knew that I was going to have to talk to an audience that is mixed. They told me general and specialists. So let me say, I'm just going to make everyone unhappy by trying to simplify how a quantum computer works. So let's step back. A lot has been said already, but so I think the question here is, so what are these quantum computers? How do they work? And why we don't have them? Why don't we have a quantum phone yet? So quantum computer, as you heard a lot already, the idea is this second quantum revolution, let's build on these very special properties that drive many of us crazy because they are counterintuitive. So our brain cannot get used to this, the concept of non-deterministic. So we have superposition, we have entanglement. They are very, very special properties. So classical computers, you all know, you have 1 and zeros. That's how we encode information. And that works with laws of classical physics, more or less. And then quantum, instead, we really want to take advantage of these very special properties. So we want to build hardware that actually, let's say a qubit, that really can encode information with these properties. And so what does it practically mean? So you want to use, let's say, something that can be not just 0, 1, but in a superposition of 0 and 1. And so there are many, many platforms today that allow you, that are under research, under active research. There is not a declared winner yet. So you can use superconductors, you can use ion traps, you can use things that don't yet exist, topological qubits that are under investigation. So there is really, really very active field. But the technology is, so Bob asks me, what's the status? Where are we at? So again, actually maybe for the very general audience, the concept here is just imagine a coin, right, that has 2 faces, head and tail. So that's your classical computer, 0 and 1. And then you flip the coin in air, you have simultaneously 0 and 1. That's what people typically like. It's more intuitive. So simultaneously, this simultaneous operation, this sort of like being more parallel than sequential, is a little bit of the advantage that we are trying to take here with building a quantum computer. A quantum computer does not, and at least it's not envisioned to replace a classical computer. It's not going to do 2 + 2. It's something that will solve a very specific class of problems. As Katiuscia was mentioning, Shor algorithm, so factorization, breaking RSA encryption, so with very, very important potential consequences for national security and more. But at the same time, very important also and close to and dear to my heart as a physicist, as Feynman said many years ago, if you want to simulate nature, you better do it with something that is close to the way nature works, which is quantum mechanics. So these computers can help, for example, really solve problems that are really, for example, particle physics or condensed matter physics that are really close to how the world works in the microscopic world. So now the question is, again, where are we at? We have a long way to go, but I think there is a lot that has been done already. So quantum computers do exist. You have processors that run and on which people can actually do computations, can do simulations. Maybe we cannot yet do things that are very impactful, but we can already, and again, there is also disagreements on, in the community on exactly how far we are. There are companies that say we have entered the era of quantum utility, meaning that we can already perform meaningful problems, maybe not more efficiently than you would do on a classical, but at the same time, you can already perform some level of computations. So, right, so that's a correct statement. So I think, again, this is really important because there has been a lot of research, and I think we have to not be anxious. We have to appreciate how much has been done already and the level of maturity we have reached. But I think it's very exciting to think also how far we have to go. Things that we are doing, for example. So we work very closely with one of the potential platforms, or the platforms that already exist, which is using superconductors. So imagine how a classical processor looks. It's a chip, right? A silicon chip on which you have all these transistors. A quantum processor looks very similar. You build it on silicon, but then you put some layers of superconductors on top, and those form your qubits. And what are the challenges today? Maybe one concept that has not been introduced yet is coherence and decoherence. I think that is one of the biggest challenges. So we talked a little bit about noise and error correction. What do we need to solve? So qubits, like for example, superconducting qubits today, they live, so they can store and perform computation, let's say, for the orders of tens or hundreds of microseconds. And then you obtain an error. So that's a problem. So how do we solve that problem? We can make many, many qubits and try to have redundancy and route information in a way that we can do what Katiuscia was explaining, error correction. Or we can also solve the problem at the root, which is, why do we have errors? We have errors because it comes from very much from the materials that you use to build these components. And so a lot of research, for example, at the center that I direct is around what's in this material that causes loss of quantum information, that causes these errors. And it really comes down to, and that's why it's so exciting, because it's really at the interface of so many different disciplines: material science, device physics, right, superconductivity. So we're really getting to the root of how the nanostructure of materials, how these layers of superconductors or even the semiconductors, why they steal this quantum information, why they steal the photons that we are using to perform the computation. And so it's very much a challenge, like an engineering challenge, a very complex engineering challenge, but also a lot of fundamental science of even understanding why certain things occur that generate errors. So maybe to wrap up so that I don't go too long, I think my summary is the technology is really already at a very mature stage. We can even see, I would say, a path to what is called a fault-tolerant quantum computer. You can go with brute force and scale up and do millions of qubits. Those are engineering challenges. But there is also a lot of revolutionary things that need to happen to bring it down to something that is a little more compact and realistic. But it's not going to be a laptop. It's still not going to be a laptop. Quantum computer is going to be a very specialized facility, maybe like a supercomputer that solves very, very specific class of problems.
Thank you. Does anybody on the panel have thoughts about where they think quantum computers will make the biggest impact? My understanding is, as Anna said, as Katiuscia said, factoring numbers large numbers can be important for cryptography. Anna mentioned simulating systems that you might not otherwise, if I understand correctly, you could not even contemplate simulating on any kind of conceivable classical computer, say for quantum chemistry, larger molecules, things for drug applications, stuff like that. Are there pet ideas that any of you have, or feelings for where quantum computing will make the most difference, or also when we'll start to see this?
I don't know. I think it's also important to mention for this audience that there is a bit of a hype in this field, so I don't want to just claim, yes, we are almost there, we are not. But also, I think even from the theoretical side, even though we have this big hope that, yes, maybe we are going to be able to use it for solving chemistry, design new drugs and so on, but that is, so far, we don't know how to do that. We don't have a clear answer. Actually, even if you look in industry, Google just put a prize out there of some millions for someone if could come up with some algorithm that it would be useful.
So even if we had the computer, we're not quite sure how to use it.
Exactly. Yeah, even if experimentally people would come up with a very controlled ways, we call qubits, the what's processing the information, if they are really, really good. From the algorithm side, also people are still figuring out what kind of problems you'd do, so that it would be better than the classical computer, at least as long as it lasts, but at least, right? But because if it's just what you can do with a classical, yeah, I mean, it's nice from the point of view of science, but if you're asking about something that is practical and useful, I think there is still quite a lot of research being done. Yeah.
Gotcha. You know, on the hardware side, the big issue is this decoherence, the fact that qubits don't last very long. You know, they're the quantum analog of bits that hold the information. And Robert, when I spoke to you recently, you mentioned that we need to do, that material science could be, you know, we need to look to material science potentially to develop the equivalent of transistor. I'm not sure if you meant, you know, better qubits or exactly what you meant, but maybe you could speak to how, you know, material science is also a very active area right now in terms of quantum technology and how that may overlap with the development of quantum computers.
Well, I think to understand where we could go with quantum computers, it's useful to look at the arc of the development of classical computers. And you can look at where classical computing was in the 1940s, and it was these big hulking machines that required many, many people to run, that were full of vacuum tubes, that were fussy, and were really not very powerful. They only had certain very bespoke uses. And what changed classical computing was the invention of the transistor at Bell Laboratories in 1947. The invention of the transistor, and then maybe the next 10 years, people doing sort of necessary material science to decide what was the best material to make a transistor out of, and they decided that the original germanium that they made the transistor out of wasn't so great, and silicon was much better. You could make it much cleaner than you could germanium, and that invention of the transistor and then its further development in the 1950s led to the possibility of integrated circuits and the computers that we have today. It was this technology that allows Moore's law to apply, where you get a doubling of computing power roughly at least in that initial period, every 18 months. And so with quantum computers, the question is, are we in the 1940s or are we in the 1960s, where, you know, through work and lots of money and investment, we can have, there's going to be a Moore's law for quantum computing, where every 18 months or every some finite time period, we see this doubling of computing power. And personally, I don't think we're in the 1960s when it comes to quantum computing. I think we're in the 1940s, and our current generation of qubits are like vacuum tubes. And so we need to do necessary material science to find the quantum equivalent of a transistor. And I think we need to find a second generation of qubits. I don't think superconducting qubits, I think there's a lot of work that can be done to improve them, but I think probably they're fundamentally limited. And I have a feeling that trapped ion, quantum computing is based on trap ions may be similarly limited, and we may need some other technology. So I think it's important that we do the fundamental material science research to investigate what materials or what physical systems could serve as a functional qubit that maintains coherence and entanglement for long periods of time, which is a key property for how useful they are in a quantum computer.
If I can add, I think in certain sense we agree, but also I tend to partially disagree, meaning that certainly the material science, as I was mentioning, to ensure that you can preserve coherence, that you don't have too often noise. But I think the comparison with classical, in the way you put it, in a sense can be dangerous, because that tends to mean in people's mind that we want to scale up, that we want to be able to have millions of transistors, right, Moore's law and so on. But I think really what matters right now is quality, right? So, and also scalability of the systems is not really around, the chip itself, right? It's around everything else. It's the dilution fridge, it's the controls, right? All these things are very, very, very large. So I guess what I want to say here is, right now we should be pencil focused on making sure that we make, let's say, 50 perfect qubits. And then we worry tomorrow, right, about, if needed. Again, it's again the concept, is quantum computer going to be something that you hold on your desk or not? And in my opinion, it's not. It's not something that will come to our everyday life and our everyday desks. And so I wouldn't worry too much about how big it is, right? But really that it performs something important, some important computation. And that is just about quality of few qubits.
Can I? Oh, I'm sorry.
Philip, you also work, speaking of material science, you work on the low-dimensional materials and taking advantage of quantum effects there. Can you talk a little bit about what you're doing there and what are low-dimensional materials and why is that helpful?
Yeah. So before hit onto this more specific low-dimensional material, I think these kind of discussions, previous discussions, extremely useful and important. So the scaling of the qubit into many qubits, as well as improving each qubit's quality, is indeed important. And having more of this robust quantum computing is around, then probably also help to develop the algorithm, because many more people start to use it more readily, and certainly it's the more of the chance we will come up with important algorithms as well. One of the limitations of the already mentioned is that decoherence is one of the main limitations of the scaling up or improving the quality of the qubits. In fact, innately with quantum mechanics as well, right? Because quantum physics is relatively fragile, then maintain the coherence of the quantum system is very important to the quantum operation. The one way that get around this kind of problem is that come up with this new platform of the developing qubits, and there is this idea of already mentioned the so-called topologically protected qubits, which means that somehow the quantum state itself is robust enough, and it doesn't resist onto the decoherence, such that you don't have to do the error corrections. And once you make this one qubit, you don't have to make another qubit to correct the errors. And that's one way to improve this the efficiency and quality of the qubits. Unfortunately, we don't have the material platform to realize those of topologically protected qubits. And a part of this quantum research is also try to find out the platform to realize those topologically protected qubits. And important part is, can we just find out quantum material that just enable those quantum topologically protected qubits? And there are several material platforms, including so-called this low-dimensional material, there where the electron is confined into the lower dimension, typically 1 dimensions or 2 dimensions, where you can amplify this quantum mechanical effect to engineer into this topologically protected qubits. And that's the part of my research is tied on. Unfortunately, at this point, no definite demonstration of these topological qubits around yet, but there has been some theoretical predictions and proposals out there to realize those of systems. And many researchers, the material physicists, including myself, is chasing around these topologically protected qubits based on the quantum materials.
All right. So if I understand correctly, the big problem with quantum computers is the qubits don't last very long, or they're very easily disturbed, and so you have to do your computations extremely quickly before errors build up and they just fizzle out. And a topological qubit, which is something that if you had the right material you could create, would be everlasting? Would it just...
Well, I wouldn't say that everlasting, but there's always some limit. But it's considerably live longer than the classical qubits, I would say.
Okay. Yeah. And what is it about? Why? So we're talking about, you said 1 and 2-dimensional materials. So like something like a string or something like a sheet. Why are those the right kinds of materials to be looking at?
It's not the shape itself, but there's this is kind of interesting part, in a sense that we are trying to kind of create a quantum machine out of quantum materials, right? But then this quantum material has kind of unique properties dictated by the quantum mechanics as well, right? So that's kind of somewhat recent understanding that often that when you have not only one electron, start kind of throw the many electrons. Sometimes it is many electrons or many particles. Start when you just treat it like quantum mechanically, some emergent properties comes around by the dictated by quantum mechanics. Often some of this part is not well understood. So it itself is a very kind of active research area that probably Robert can mention a little bit more of the theoretical perspective. This type of the new quantum mechanical properties coming from the emergent phenomena itself is interesting, the quantum properties, and we are trying to use that to just kind of build the quantum machines, and that potentially this quantum machine allows us to kind of find out more of these materials again. So I think there's kind of interesting feedback can happen, hopefully, indeed.
Gotcha. Why don't we go to the last chapter of our talk tonight, which is getting back to what now we've talked about things that people are doing with quantum theory and all the things we understand about it that we can potentially use to do cool new things. This question of what does quantum theory mean? What does it tell us about the world? David, could you maybe start us off by telling us why is this even a question? Why is there since the founding days of quantum theory, there's been controversy about what it means? How could this be? I mean, we're doing all these very sophisticated things with it. How could there be so much doubt about what it says about the world?
There are certain stories that we feel like we need to tell with our physics that it's not clear how to tell with quantum mechanics as the fundamental physics of the world. So once again, say I have an electron which is in a superposition of being over here and being over there. And like I was saying before, we think we have reasons to believe, we think we have compelling and empirical reasons to believe that it's wrong to think of the electron as being here, and it's wrong to think of it as being there in these circumstances, and it's wrong in more subtle ways to think of it as being in both places, and it's wrong to think of it as being in neither place. Indeed, we think we have compelling and empirical reasons to believe that the very question of whether the particle is here or there doesn't make any sense. And yet, our experience in the laboratory is that whenever we go and look for this particle, we invariably find it either here or there with certain probabilities that we can predict from how the state of the particle was initially prepared. So it seems, at least on the face of it, that the very act of looking for this particle seems to somehow transform it from a condition in which it doesn't make any sense to ask where it is to a condition in which, in fact, it's either here or there. And there's a question, like I said before, of how to tell the story with this theory of how this transformation takes place, of how the mere act of looking or measuring or something like that manages to bring about this kind of transformation in the state of the particle. For a long time, the dominant way of thinking about questions like this, and this is a view that emerged and was disseminated under the very powerful intellectual charisma of Niels Bohr, was a view according to which physics is not meant to go that deep. And physics is not the place where you should be looking for answers to questions about how the world fundamentally is. Physics is the place where you should be looking for answers to questions about how certain particular experiments are going to come out. And if you've got it doing that for you, you should be thankful, and you shouldn't ask for more than that from the physics. And this is what these slogans like "shut up and calculate" are about. I would say over the past 30 or 40 years, I mean, this has been going on since the beginning, especially in connection with figures like Einstein and Schrodinger and so on, who were very unhappy with this Bohrian kind of orthodoxy. But it's been going on in a much more collective way than that, and as a much more ongoing project than that for about 40 years now, I would say. And people want to learn how to tell a story like this in the context of quantum mechanics. And people do want, after all, one of the things people do want from physics is an account of what the world is actually like. If you want an account like that, and the problem of constructing this kind of an account is what I was alluding to before as the measurement problem. And just to give you a little sort of status report, there are nowadays 3 very different, very much discussed, quite serious ways of approaching this problem. And these 3 different ways of approaching this problem end up painting vastly different pictures of what the world is really like. So let me just mention them. To begin with, there's a set of theories of what are called the collapse of the wave function, which cleverly modify in small but important ways the standard laws of quantum mechanics in such a way as to explain concretely, mechanically, how this mere act of looking might bring this kind of transformation about. There's another tradition of theories called many worlds interpretations of quantum mechanics, according to which it's not the particle, but rather us, that undergoes a peculiar sort of transformation when we look at a particle which is in a superposition of being here and there. On this way of thinking, the idea that our looking at the particle somehow snaps it out of its superposition of being in here and there, which is what goes on in these collapse theories, on this way of thinking, that's all wrong. What happens, according to things like the many worlds interpretation, is that the act of looking at the particle transforms not the particle, but us. It's not the particle that gets snapped out of a superposition, but it's us that gets snapped into one. So that it now appears to us falsely that the particle is either here or there. And then there are so-called hidden variables interpretations of quantum mechanics. The most successful of these, the most well-developed of these, is an old theory due to David Bohm, first published in the 1950s, but ignored for many, many years, rediscovered by the famous John Bell, who focused a lot of attention on it. In these ways of thinking about quantum mechanics, there never were any such things as superpositions in the first place. The electron always was, in some way that we couldn't see, in some way that was hidden from us, either here or there. And all we do by looking is to discover where, in fact, it's always been. All 3 of these approaches are, insofar as we know at the moment, live options. There's a lot of work to do on them, making them, for example, consistent with the theory of relativity. All kinds of trying to develop them in such a way that there can be clear experimental tests discriminating between them. And Professor Bassi, who was one of the organizers of this workshop, has been a leader in this kind of work, attempting to experimentally discriminate between these various different interpretations. But anyway, all of them are being very actively studied in a quite serious, rigorous, scientific way. And a great deal of effort is being devoted, in particular, like I said, to the design of experiments that might be able to tell them apart.
Yeah, thank you. Thank you for that. So David has just painted this picture of like these alternatives. Like one alternative is quantum theory tells you to shut up and calculate, stop worrying about how the world really is. And then there are these three other alternatives that he mentioned that are, sometimes called realist interpretations of that.
And
We
hope there are going to be more.
Yeah, and there could be more. Right. There are three possible pictures for how the world really is to explain the weirdnesses of quantum theory. I'd love to hear from all of you about whether these kinds of those distinctions make any difference to you in your work or in just the way you think about quantum theory, and whether it matters to you, because there are wide variations in terms of what people think about these things. So. Maybe I'll start with Robert. Robert, you already tipped your hand. I think
Oh, okay. So yes, I've already said I'm a professional physicist, so I have not spent. I'm actually rather. I do not have a very well-informed opinion between those three possibilities. But I had the pleasure of listening to an old podcast between David and Sean Carroll about a week ago, and they talked about the different possibilities here, but they spent most of the time talking about many worlds theory. And it was clear to me from the podcast you did not like many worlds theory. But you didn't really get a chance to talk about wave function collapse or Bohmian theory. And so I would actually be interested in asking you, what is of these three possibilities, what do you think is the most coherent?
The worry about many worlds is, at the end of the day, whether it's even internally logically coherent. That is, whether or not it's not literally self-contradictory. And I have that worry about many worlds. The podcast was mostly about many worlds because Sean is very fond of it. But vis-a-vis the other two, I don't. First of all, the nice thing about the other two, that is these collapse theories and this Bohmian hidden variables theory, is they are unambiguously, straightforwardly, empirically different. They make different predictions about how certain experiments are going to come out. The experiments we would need to do, which involve measuring interferences between macroscopically different states in highly dissipative environments, these experiments are very, very technologically difficult to do. Some of the challenges in doing these experiments are the same challenges people face in trying to avoid decoherence in quantum computation, and so on. But they're much more daunting in this case. So these experiments are very difficult to do. But in a case where we've got two theories that are empirically different from one another, the appropriately epistemically modest thing to do is to say, how the hell should I know? This is up to nature. We've got to do these experiments and find out. I do think there are different, quite exciting things about both of these theories. I think that if one of these collapse theories turned out to be true, for example, it could quite profoundly change our understanding of how statistical mechanics works. It could also suggest places to look for possible violations of Lorentz invariance, of the special theory of relativity. So the collapse theories are interesting for all kinds of reasons in that way. The hidden variables theories, I think, are more mathematically elegant. Sometimes that's cited as a point in favor of a particular view. But yeah, like I say, so among the three views, there's one whose internal coherence I have worries about, whose internal coherence I have doubts about, and that was the subject of most of the conversation you heard between me and Sean on that podcast. For the other two, we've got two pretty viable scientific theories here. There are questions for both of them about exactly how to turn them into versions not of non-relativistic quantum mechanics, but of relativistic quantum field theories and so on. I don't see any obvious obstacles in either of those cases, but there are technical challenges about exactly how to do that. And like I say, the collapse theories have real cool consequences if they turn out to be true for statistical mechanics, for Lorentz invariance. But this is a decision of nature's, not of mine. I think both of these theories are well worth developing and studying and seeing how to make compatible with special relativity and so on and so forth. But the urgent thing to do, although I suspect it's a long way off, and Angelo knows more about this than almost anyone else in the world, the thing one is waiting for are the experimental tests.
Yeah, I think it's kind of very good point. I think measurement kind of theory or measurement assumptions that I have in the quantum mechanics is aware that students, when I learn these things, they should have calculated problem sets. Right? That's kind of really, in some sense, unsatisfying, that kind of telling the stories. Part of the reason that was kind of really difficult, just kind of take the assumptions and starting point is, when it comes with the measurement, basically you have the one particle of this, the quantum particles interacting with macroscopic experimental instrumentations. There's not much of the descriptions sensible description we can make easily. But now I think some of this measurement can be done with a much more controlled set of this kind of control set of the particle, even if it is macroscopic states, such that experimental accuracy is possible, so we can dissect this measurement with a little bit more detail. I think this superconducting qubits is a good example, right? So I think some of this kind of the assumptions can be under the scrutiny, that potentially this can be really quantitative science, quantitative physics we can just do, experimentally testable based on this technological development. I think that may shed kind of really big light into our deep understanding of quantum mechanics. That's actually some of the hope that I have, and that's kind of our first step to understanding this many particle quantum system, including the kind of entire universe. The very first steps can be done. I think there might be another big steps we may actually anticipate in the near future.
Yeah. Other thoughts?
Now, in my case, again, I'm an experimentalist, so I don't have strong opinions, but I can maybe just say that our center is mostly focused on, take what works, right, and just go ahead and build these quantum computers. But we do have also, at the same time, really trust where we bring in theorists, such as David, and we put them side by side with experimentalists and see if we can use some of these qubits we play with, to test indeed the more fundamental laws of quantum mechanics. We work, for example, with David Kaplan and Surjit Rajendran from Johns Hopkins. They have theories of, is it possible that the assumption is that quantum mechanics is linear? What if it is non-linear? And can we test some of these non-linearities? And we are literally putting these theorists side by side with our experimentalists to do some of these tests. And we'll see what comes out, but that's very exciting. I mean, we have a path of, engineering, very exciting engineering challenges, and at the same time, pushing these technologies may come back with the much more fundamental and important answers.
Yeah, I don't know, maybe I think I do have a strong opinion. So, yeah, so to me, when I think of what you want from a theory is kind of this, wouldn't say calculate and shut up, but it's really, you want some compact description of what you are measuring, and you want to be able to make predictions of new phenomena, and then you go on and try to check those in the lab. So if you have that, this is already great. But from that to making the leap to say, oh, this is the description of reality, I think this is huge, and I don't think necessarily you need that. But I would say that all theories, they have a limit of validity. So I think for this audience, I would like to say that it's not that we're saying, oh, there is so much in quantum mechanics is incomplete, we don't know many things. I don't want to give the impression that it's this wish-washy theory, because it's not. It's actually one of the best physical theories that we have out there. Like, it's extremely predictive in many ways. So, and this is not just quantum. So, for example, that there is a limit of validity that we know very well, right? All theories are like that. So there is dark matter out there that we don't know what it is, and this has nothing to do with quantum as far as we know. So there are all the theories that have some issues that we are trying to figure out. And this is science. That's how science evolves. It's okay. So I think this is actually exciting that there are things in the theory. But of course, I do love to see that people are coming up with other ways of understanding quantum, as long as this is compatible with all the experimental evidence that we have so far. And I think these outside-of-the-box ideas, they are always useful to gain new insight and to deepen our knowledge of things, to see from other angles. And yeah, eventually it can lead to new theories, new understanding. But so in this sense, it's always nice to have those not the mainstream physics, right? So this is it's good, but it doesn't mean that you have a theory that is failing us. I think in many ways, quantum theory is awesome. We know a lot from it. So, yeah.
Yeah, there's no evidence whatsoever at this point of any failing of quantum theory ever failing in any experiment yet so far, and it's been tested to a great degree.
I mean, in general, in the universe, there are many things that we don't know.
Yeah.
But I wouldn't say necessarily, oh, we did this experiment, this is showing that quantum mechanics is wrong. Yeah, that we...
But it could happen.
Yeah. It always can, right? Yeah. It's how we turn out seeing that classical mechanics was not enough. It was how Einstein came up with with Einstein was a different story. But anyway, so we use relativity, and all of that are new theories that appear as we find out a new phenomena. Yeah.
Okay, great. Why don't we go to Q&A? We're kind of in the last 10 or 15 minutes here. I guess you can raise your hand if you have a question. I think we'll bring a mic to you. Right over here? Right here. In the second row? Second row right here.
Yeah, great presentation. Thank you. I wanted to ask, why do you think we have not made any progress, or very little progress, on quantum gravity and unifying the two main theories?
That's a tough one.
Well, I think it's because in order to regimes where quantum gravity will be important are regimes that are fairly hostile to human life. I mean, we need to get near to a black hole to see corrections to Einstein's theory of gravity, and it's there's no black holes nearby, and so it's going to be hard to we don't have really precise experimental tests of potential theories of quantum gravity. I mean, certainly the potential candidates like string theory, which predicts that we don't live in a three-dimensional world, but we live in a 10-dimensional world. There's been little flurries of excitement where we've imagined that these 10 dimensions, these extra dimensions beyond the 3 that we perceive, are actually not, the way string theorists explain these extra dimensions is that these extra 7 spatial dimensions are wrapped up very tightly, and so the length scales associated to them are so small that we just can't detect them. But there was a flurry of excitement 15 years ago or so, where certain theorists posited that these wrapped up dimensions were actually a little bit larger. And if they were a little bit larger, there would be corrections to gravity. And there was some attempt to try to detect these deviations from the standard theory of gravity. But those failed, or they didn't see anything different than what we expected. So I think it's really part of the problem is that we don't have good experimental guidance here to discern between different competing theories, or to suggest new ones. There's something called loop quantum gravity, which is also one of the possible candidates, but I don't think we have really good experimental means to distinguish between these two.
Yeah. And wearing black, I can't see him, but yeah.
So there's a lot of rigorous research need to be achieved at quantum advantages. When it comes to research, it's come with funding, right? And what advices can you give to young researchers in the room? How can you convince investor and government to put money on the line right now instead of holding up for a couple more years?
Sorry, can you repeat the question again? Is what advice for?
The question is can you stand up, please? And this is about investment in what?
Yes, so raising awareness about quantum and its importance is really like what we're aiming for to expand in the communities. So what advice you can give to young researchers in the room how to get funding for their research projects?
Funding for research.
I think the advice that I always give is that you need to be, I got a big funding, right? I'm PI of a mega grant, $150 million. And I would say the reason I won that grant was because I was a specialist in an area that is very important for the advancement of quantum. So I think the advice I would give you is to specialize, not in everything, right? Be really specialized in one thing that is really important. Pick one aspect and be that person that is the only person that can solve that challenge.
Any other thoughts on that? All right, we can go to somebody else. In gray over there, maybe?
Thank you. So with the quantum entanglement theory, is there a way to experiment or magnetically attract one particle from, let's say, this universe from another particle that's quantumly entangled from another universe?
Thank you.
I don't know. I mean, there's lots of pretty loose talk, I would say, about, this is in parts of the string theory community, actually, about what's called ER equals EPR. Einstein-Rosen bridges are somehow closely connected with entanglement, with entanglement of the kind that is dealt with in the famous Einstein-Podolsky-Rosen paper. And there's a lot of thinking that entanglement can play some kind of role in knitting disparate parts of space-time together. This is very, very far from the stage where anything like an experiment is being proposed. These are speculations which, to the extent that I've studied them, I have a really hard time understanding. So, I mean, the honest answer was, I don't know.
Any other questions?
Hi, as a science communicator, I find that quantum physics is one of the fields of physics where there's the biggest mismatch between what the public understands about what's happening and what's really happening.
We had the demonstration tonight.
No, of course not. It's intrinsically difficult for things like quantum gravity. It's understandable because we really have no idea. But for other things, like more applied things, like when is the quantum computer coming, or things like this, do you think it's a problem? Do you think we should do something about this? And any thoughts about what we can do?
Anybody?
Maybe I can start with. So I think it's probably a matter of the time and kind of more of the exposures. I think to me that some of the classical physics, say electromagnetism, no one actually thinks this is counterintuitive, is strange. But in fact, if you start kind of teach and then kind of start to think about, that is in some sense rather counterintuitive as well. So all this kind of vacuum is filled with electric field and magnetic field, arrows kind of floating around and emitted from the charges and can communicate it. And all these things is rather, in some sense, when you first hear that nothing know about it, it's rather counterintuitive. But nevertheless, I think no one is saying that this is classical physics, counterintuitive. And in fact, we are using cell phones and all of these things as a rather naturally, right? In some sense, quantum mechanics is only 100 years old. And over the time that we got exposed to more of these things and more of the applications based on quantum mechanics, at some point that we start to develop more of the kind of intuitions out of it, and any more of this feel like the disconnections from that what is kind of being developed and what is being said versus what public perception. In some sense, over the time that as we got familiar with all the electromagnetic theory, eventually quantum mechanics is basically kind of very close to us. And in some sense, we may develop our quantum intuition eventually. That's my hope.
I think me and you talked about this before, if I'm not mistaken, and your answer was that we need to train scientists to be better communicators, and I actually agree.
A loaded question. I think we got somebody in orange over here.
Hi, so I'm wondering, how long do you think will probably take for the quantum technology to really have impacts on our everyday life, like the electronics do? And also, because as we can see right now, like very often when we talk about quantum technology, people talk about like the development of quantum computing, as well as like, for example, the superconductions for quantum computing. Like, if it makes me feel like a lot of the hope for the application of quantum physics or quantum technology are about quantum computing. So I'm wondering if there are any other areas that also has a lot of hope that people are putting into for the application, for the future application for the quantum technology.
Well, let me say first of all that I think quantum is already having a huge impact. So maybe not in the way you ask, which is, the electronics that changed everyday life for all of us, but I can say that when the National Quantum Initiative in this country started several years ago, our funding agencies came to us and said, come on, let's move a lot of the workforce at the national labs and more that's directed towards this quantum revolution. And I think that was super exciting for all of us. It kind of sparked new enthusiasm. And that's already impact, because we started developing new technologies, we started to do new experiments that had, I would say, indirect impacts, but very positive ones. And we recruited a lot of young folks that came to science because people, smart people want to do exciting things and technologically challenging things, and that again is impact, right? So I think there is already impact, but in the sense that you ask, you can read many articles and people have different opinions from being within my impression is less than 10 years, we'll see impact of quantum computers. That's my guess. And sensors are lower hanging fruit. Sensors will be earlier than that.
One more over here, great.
Do you think it's possible that particles could be a byproduct of humans?
Could you say another sentence? How do you, first of all, goes without saying, there are plenty of particles that are byproducts of humans. I'm not sure I know what you mean.
I guess what I'm questioning is if when people say, let's say you can manifest your reality, right? We've had a lot of talk about that now. Do you think that, because you were speaking upon prior how, okay, let's put this in a simpler, straightforward. So if we can create our own reality in a sense through thoughts and waves, theoretically, that is possible to do, and people theoretically have done it, is it possible that we can create particles?
That's literally
You're
our
asking a
job
it's a
at
hypothetical
Fermilab.
question.
We smash particles.
Because you talk about how, like you said, Kat, how when you start to measure quantum, you're just basically breaking it. Because every time you start to measure, it's almost unmeasurable. So is there a way for us to almost redefine what it means to measure the quantum world?
So I don't know. So you said something before. I don't know if this is what you're talking about, but it seems to be connected to what is the role of the observer in quantum mechanics. I don't know if this is what you want to hear about. I can't connect that to your first question on how this is related to creating particles and connected to what. That part I don't get. But what I can tell you is, yes, that the observer has a role in quantum mechanics. So even when we talk about entanglement, for example, if you want to kind of verify the correlations connected to entanglement, people have to, well, not in that way, but you have to know what kind of measurements you are doing to your system, so that then you can compare correlations and then you get to see the entanglement there. So if you do random measurements you have two entangled particles, let's say. If you do random measurements in one side and random measurement in the other, you're not going to see the correlation. So in this sense, the observer has a role. But I cannot connect that to your question of the particles. But yeah.
Yeah, I mean, I think you could imagine that you had a state which was a superposition of something with two particles, something with one particles, and then something with no particles. And according to the standard interpretation of quantum mechanics, when you look at it, you have to see a definite number of particles. You can't see 2, 1, and 0. You have to see 0, 1, or 2. And so by the fact that you look at it, you're going to see some definite number of particles. And that, in some sense, I mean, you fundamentally change the state. So in some sense, you could answer your question, yes.
I think I've been remiss on this side, but I haven't really seen any hands. So one more chance for this side. Does anybody have a question?
Maybe this is not even a question, but what's a particle? And is a particle a particle? Thank you.
Questions, no?
This comes back to how the world really is, right?
I mean, well, it depends a lot. I outlined 3 ways of trying to solve the measurement problem that are under investigation. Turns out that if you ask seriously, what do you mean by a particle, it's going to have very different answers on those 3 ways of solving the measurement problem. The one that contains an idea of a particle that's most similar to our classical idea of a particle is this hidden variables theory in the Bohm that I mentioned. In something like GRW, the notion of a particle is going to on some level be vague. The relationship between particle talk and talk at the fundamental physical level is going to be something like the relationship between particle talk in classical mechanics and talk about tables and chairs or pressures and temperatures or something like that. There's going to be a vague connection. Particle language is not going to turn out to be the exact fundamental language of the world. Like I say, in Bohm's theory, it is still going to be an exact language. In many worlds, I don't know what's going to happen. But yeah, I guess there is a serious question there. And insofar as we understand things at this point, that's going to depend on what turns out to be the right way to solve it.
All right, I
But
think.
in an experiment, it's something that will make a click in the detector. That's a particle.
Something countable.
All right. I think we've used up all of our time. Could we please just give a hand to all of our panelists.